Swayam Prabha. Digital India. Educated India.
is that we replace that enthalpy of combustion as heating value of the fuel and become, which is very widely accepted, and it is always a positive number and which is equal to magnitude of enthalpy of combustion. That means whatever during a chemical reaction, whatever magnitude of enthalpy of combustion, that is assigned as the heating value of the fuel. Now there are two heating value of the fuel can be possible. One is at lower heating value, other is the higher heating value. So during a chemical reaction, what may happen is that combustion products are formed, they are already at elevated temperatures, and we know that during the combustion process always water is one of the entity. Now this water at that elevated temperature will exist in vapor form. So if you calculate the heating value of the fuel during a combustion process, we assign it as a lower heating value. Now when these combustion products are released from this combustion environment to atmospheric condition, it is basically cooled. So when it is cooled, the water vapors try to condensate, and when all the water vapors try to condensate, that means similar amount of heat is also released. So that number is assigned as a higher heating value. So higher heating value of the fuel is defined when all the water vapors formed during combustion chemical reactions is in the form of liquid state, and when lower heating value is recognized when all the products are in the vapor state. When the gaseous products of the combustions are cooled at constant mixture pressure, the dew point temperature is reached. So when water vapors begins to condensate, this will cause the condensation, that is deposition of water, and that means in other words we can say higher heating value of the fuel exceeds the lower heating value is nothing but the difference in the energy that will be released. So here in the final note we can say whatever HRP we get is a enthalpy of combustion is always a negative quantity, and we assign that as a positive number as the heating value of the fuel. Now whatever we have discussed so far, we will try to solve a numerical problems based on the concepts that we covered today. At the learning components we covered about mainly on enthalpy of formation, enthalpy of combustion and heating value of the fuel. So based on this we will try to solve a problem which talks about a methane and air combustion system in a simple gas turbine unit. So if you look at a gas turbine unit, typically we have a compressor. That compressor is coupled with a turbine, and fuel is introduced in a combustor. So we say, and the combustion products comes and enters into the turbine, and when they expand in the turbine we get power output, and there is entry, air enters into the compressor and fuel enters to the combustion. And if you treat entire things as a control volume, then we can say there are two entries, one for air, other for fuel. There is one output, that is a combustion products, and this combustion products goes out. And what are the things that has given to us? This fuel is methane, CH4, and it enters at 1 atmosphere 25 degree centigrade. And we have air or oxidizer is air which is O2 plus 3.7276 N2, and we are saying it is 400% theoretical air. Then when you say combustion products, it is at 457 degree centigrades, and this 457 degree centigrade is about 730 Kelvin. And this oxidizer is also oxidizer at same conditions as that of fuel. So, this is 1 atmosphere 25 degree centigrade, and what is given is the fuel flow rate m dot f is 3 kg per second. So, we know the molecular weight of fuel, that is CH4, that is 16. So, we can find out n dot f. Okay. So, if this is the problem, the first thing that we need to do is that we have to write the balanced chemical reactions. So, the main reaction we can say CH4 plus 2 O2 plus 3.76 N2, it is supposed to give CO2 plus twice H2O plus 7.52 N2. So, this is the balanced reaction. Now, with 400% theoretical layer, what the reaction is going to be there? So, we have to write it as CH4 plus 4 times into 2, means air is supplied 4 times that of fuel, 3.76 N2. Now, it will give you some number. We do not know what is this, ACO2 plus BH2O plus CO2, because it is excess air. So, it means higher oxygen, C times O2 plus D times N2. Now, we have to make the mass balance or species balance. By doing this, by doing for carbon, we say A is equal to 1. For hydrogen, we say twice B is equal to 4. So, it will be B is equal to 2. For oxygen, we can write B plus twice C plus twice A is equal to 16. 4 into 2 into 2, that is 16. So, we know B and A. So, this will give you C is equal to 6. Then for N2, we can write twice D is equal to 4 into 2 plus 3.76 into 2. 4 into 2 into 3.76 into 2 and 2. So, this will give you D as 30.08. So, we get this equation to be rewritten as CH4 plus 8 O2 plus 3.76 N2 will give you CO2 plus twice H2O plus 6 CO2 plus 30.08 N2. Now, we are in a position to write the energy balance. So, energy balance, because it is a turbine complete systems. So, heat comes from the fuel, work comes out from the turbine. So, you can write down Q dot Cv by N dot F minus W dot Cv by N dot F plus HR bar minus HP bar is equal to 0. Now, what other information is given is that heat transfer from this engine is 6% of net power. So, we can say Q dot Cv is equal to minus 0.06 W dot Cv, because heat is coming out, W work is also coming out. So, there is a negative sign here, and other parameter we can say, and this number will be, we can write 1.06 W dot Cv by N dot F would be HR bar minus HP bar. Okay. So, now we are going to find out what is this HR and HP. So, to do that, what we need to know we have to write down this equation. What is HR bar? For HR bar, we can say it is for reactants, that is molar enthalpy of reactants. Reactants consist of methane, oxygen, nitrogen. So, the enthalpy of reactants can be found out as HFO bar plus delta H bar, that we have to write it for CH4 plus, that is 8 times HFO, that is molar number for oxygen bar plus 30.08 times HF bar O plus delta H N2. So, here we can see that all are at both reactants, and both reactants, that is methane as well as air, they are at same reference condition 1 atmosphere and 25 degree centigrades. So, we can simply assign this delta change value to 0, and oxygen, O2 and N2, they are stable components. So, we can assign this 0 for their enthalpy of formations. So, what left out is HR bar is equal to is nothing but HFO CH4, and that is at 25 degree centigrades. So, this data table will give you this value as minus 74850 kilojoule per kg mole fuel. Now, similarly for products, H bar products consist of CO2, H2O and N2. So, similar expression we can write HFO plus delta H bar, that is CO2 plus twice times HFO bar plus delta H H2O plus 6 times HFO plus delta H bar, that is for O2, plus 30.08 times HFO bar plus delta H bar N2. Now, here what are the things that we can assign to 0? Enthalpy of formation for stable component, these numbers to be 0, and this N2 is a stable component, so this will be 0. So, what is left out is these numbers, and this you have to calculate these conditions at 730 degree Kelvin. So, at 730 degree Kelvin, the data table will give you HFO CO2 is minus 393,520, all are in kilojoule or kg mole Kelvin. HFO bar for CH4, that number is minus 74850. Then we have HF bar enthalpy of formation for O2 delta H, we require delta H bar for CO2 is equal to 19258. Then delta H bar O2, this number is 13495. Delta H bar N2 12860. So, you have all number CO2, delta H, H2O, we do not have H2O, delta H, H2O. So, delta H bar H2O is 153314. So, this is the data table. So, by inserting this we can get the final number as Hp bar is equal to minus 74850 kilojoule per kilomole fuel, and HR bar is already known, is this is wrong. HR bar is minus 74850, HP bar is minus 359475 kilojoule per kilomole fuel. So once you say this, then we can find out from this equation about W dot Cv is equal to 5181 kilowatt. So this is our requirement, that we need to find out what is the net power developed by the fuel. So of course here you have to your N dot F you have to find out from the molecular weight, m dot F by molecular weight of fuel. So that is 0.3 divided by 16. So if you put this in our last equation, which was we have written as 1.06 W dot Cv divided by N dot F is equal to HR bar minus HP bar. So that equation, when it is with this data, we can get W dot Cv. So this is all about the problem that is associated with the power developed in a gas turbine combustor, which mainly uses methane as the fuel. The next problem is about the calculation of enthalpy of combustion of gaseous methane at 1 atmosphere and 25 degree centigrades. And here we need to calculate the enthalpy of combustions for gaseous methane on two conditions. One is when the liquid water is in the products, and the other is water vapor is in the products. So to do that, so it's a question number 2. To do that, first thing you have to write the methane air reaction. So methane air reaction is CH4 plus twice O2 plus 3.76 N2 will give you CO2 plus twice H2O plus 7.52 N2. And here we say that both reactants and products, they are at 1 atmosphere and 25 degree centigrades. So enthalpy of combustions is defined by H bar R P, that is molar enthalpy, and that is nothing but, in this case we can write H bar CO2 plus twice, there is 2 mole, H bar H2O minus for reactants H bar CH4 plus twice times H bar O2, and this nitrogen will cancel because both sides we have same number, so it will be minus. Now rest each of these enthalpies needs to be expressed with respect to their formation part. So we can write it as HFO plus delta H bar CO2 plus HFO plus delta H bar H2O, this is 2 times, minus HFO plus delta H bar CH4 minus twice time HFO plus delta H bar O2. Now let us see what we can assign, and they are at 1 atmosphere and 25 degrees. So stable compounds, they will vanish. So stable compound will vanish means this number will vanish. and other points, other components like delta H will vanish because reactants and products at same temperature, that is 1 atmosphere and 25 degree centigrade. So, this number will vanish, all delta H term will vanish. So, we will land off having 3 terms, is HFO CO2 plus HFO H2O twice times minus HF bar O CH4. We have to refer data. This data has to be referred at 25 degree centigrades. So, that number we can write it as HFO CO2 as minus 393,520 kilojoule per kilomole fuel. Then HF bar for H2O. Now, here we have water in liquid form, so we have data for liquid, and HF H2O data for vapor. So, we will have two numbers minus 285,830, other is minus 241,820, same unit. Another number, this enthalpy of formation for methane, that number is minus 74,850. So, we have all the numbers, we can insert it, then we can find it out. First part, liquid water in the products. So, we can calculate this was enthalpy of this number is minus 890,330 kilojoule per kilomole fuel. Second part, water vapor, which is HRP is equal to minus 802,310 kilojoule per kilomole fuel. So, we can assign it LHB, lower heating value of CH4. Lower heating value with this number we can write it as this negative will be positive number. So, it is 802,310 divided by its molecular weight 16. So, this is 50019 kilojoule per kg fuel. HHB for CH4 will have 890,330 by 16. So, this number would be 55507 kilojoule per kg fuel. So, what it means that at 25 degree centigrade, the lower heating value of methane is about 50 megajoule per kg of fuel, and higher heating value of methane would be about 55 megajoule per kg fuel. So, remember this was taken at 25 degree centigrades, and that point of time for this our simplicity, this delta H value was neglected because both reactants and products they are at same temperatures. Now, if I ask you to calculate the reactants are at 1 atmosphere and 25 degrees centigrade, products are at different pressure and temperatures, then we have to, the problem will be more complicated. This delta H terms has to be evaluated with respect to that product temperatures, and during that point of time these numbers will also be different. But however, for the simplicity of problem solving, it was simplified that we have assumed that both fuel and air, they are at same temperature and pressures. So, this is all about the lecture for today. Thank you for your attention.